So what I believe, to understand the physics properly, it is very, very important that you understand some concept pretty well, right? You must develop a approach of solving the questions. So these questions are of such kind, like for example, this question, this is a very good question. Now let me solve it, right? Okay. So it says a horizontal bar fixed at one end. So let's make an horizontal bar. Okay, so this is a horizontal bar. In physics, it is very important that you draw some sort of a figure. It helps you understanding the question well. So it is fixed at one end. Okay, very well. The length is 1 meter, right? And the cross section area is of 100 square. Is elastic modulus varying along its length as given by, so Young's modulus is given and it is given as a function of x. That means here in this question, the Young's modulus is not constant. The Young's modulus is not constant, but it is varying with respect to the x. Okay. An axial tensile load of 10 kilonewton is applied. Axial tensile load of 10 kilonewton is applied. The axial displacement of the free end is. So we need to find the delta. Now I tell you guys, so we must have seen only one formula to finding the deflection of a body or a component subjected to the tensile load. And what is that formula? This is FL upon A. Force into length upon area into Young's modulus. Now, in this question, what is different? What is the difference from the other question? So the difference is in this question, the Young's modulus is not constant, but it is varying. And while you were reading this chapter, or you might read this chapter later or sometime in some point of time, you will find that you are already doing this thing, but you haven't done this thing, but similar sort of thing you are doing. Okay, like if I give you the example, all of us, while you go through this chapter, you did the self weight case. Okay, I hope if you have learned this chapter you can relate with me. Okay, so the self weight case we have done. In the self weight case, what happens that the load is varying due to the self weight. In this case, the load is not varying, but the Young's modulus is varying. Now, have my tip. Whenever in physics you find something in a variation, right away you take the strip. Whatever is varying, if something is varying, okay, along some length or along some area or along anything, whenever something is in variation, you always prepare yourself for integration. So for that you must take the strip. Okay, now we are taking a strip here. So this is strip of a very small length, let's say this is dx. Okay, now see, once you take the strip, see in physics we have limited formulas. The only challenge is that how we are going to apply that particular formula for a given problem. Okay, like for example, in this case, the elongation, we have only one formula, FL upon A. Now see, when something is varying, what we do, we can write the same formula for the strip. Let's write it. Because see, what is the beauty of taking the strip? That as a strip, you can ignore the variation, right? You can ignore the variation. So it becomes d delta and force is F only. Now the length I'll be, because I'm writing the deflection for the strip, so I must take the length of the strip. So dx is what? This is a very small amount. Now what is area? Area is constant. Let it be like this. And E is the Young's modulus. Okay. So this is also there. Now see, we have d delta is equal to F dx upon A. Okay. F dx upon A. Now see, if I am going to integrate, if we integrate this relationship, so this is the elongation of the strip. So doing the integration, you will get the deflection of the whole of the bar. So if I integrate on the left hand side, I'll be getting delta. And if I integrate on the right hand side, so whatever is constant, you can take it out from the sign of integration. And whatever is given as a function, you can place it in the integration sign. So it is 100 e to the power minus x. Okay, now further what we can do, we can take this 100 also out from the sign of integration and we will be left with f upon 100 dx e to the power minus x. So definitely it will become e to the power x. Okay, so this deflection will become Now let us put the value. So F is given as 10 kilonewton. So this is 10 into 10 to the power 3, okay, upon 100. And what is the area? Where is the area? So it is 100 square. Now please take care of the units because we are going to put the length in meters. So I must change this square into meter. So this will become, guys, 100. So square means 10 to the power minus 6, 10 to the power minus 6. And what is the integration of e to the power x? It is e to the power x only. And what shall be the limits in which I must integrate? So see, x varying from 0 to 1. So can I integrate it between 0 to 1? Yes, sir, right away. So if we integrate this between 0 to 1, so I can write like this. So this will become delta. Now we can do some cancellation. So see, 10 to the power 4, 10 to the power 4 is gone, and it will become e to the power 1 minus e to the power 0. Okay, e to the power 0. Okay, and see, I have placed. So, what is the unit of this E? It is GPA. So, I need to multiply 10 to the power 9 also, na, right? Into this because it is in GPA. So, I have converted the force in Newton, so which is 10 kilonewton. So, 10 into 10 to the power 3. We have placed this 100. So, this will be 10 to the power 9. So, now what we are getting? So, 10 to the power 3. Right. Okay, 10 to the power 3 will be getting. So 10 to the power minus 9 it will become. How come, sir? Because we have to place it here now. Because E is the always take care of the unit. Okay. Okay, so this will become 10 to the power 9 here. Right. So it will go 10 to the power minus 9. So from here, we are getting 10 to the power minus 3. Now, see, you must know E to the power. Okay, so E to the power 1 is 2.73, isn't it? It is 2.73, 2.71 nearly. E to the power 0 is 1 into 10 to the power minus 3, and the unit is meter. So what we are getting? We are getting 1.71 into 10 to the power minus 3 meter. That means we are getting 1.71 mm. Okay. So see how I have solved this question, guys. So the key point is whenever you see something is varying, something is variation, be it E, and we have done the same way. We have done the same way in the case of the weight, the self weight case also. Right? In the self weight case, the load was variable. In this, the Young's modulus is variable. So anything that is varying, like if you go to my video on this channel, I have solved you, I have given you the self weight, I have given you the tapered bar also. Okay, and now this question also in which the Young's modulus is varying. So remember this point of mine of physics. Whenever you see something in variation, you always take the strip and you prepare for integration. And how we can take up the integration? You take the strip, whatever formula you know, you write that formula on the strip, then you integrate the formula between the limits you are having, and definitely you are going to approach to the right answer. All right. Okay. So this is how we can solve this a very good question. So see, when you solve these kind of a good questions, definitely it is going to help you enhance your concepts of physics, and it will give you confidence also. Right. Okay. Okay. So I hope you have enjoyed solving this question.